Okay, so we left last time discussing about cellular solids with these two statements. The first, that the cell shape and distribution, it has a relevant effect on overall properties of the cellular solid, depending also on the base material which is used. And the second one, that is the cell size, it has a lower effect on the overall mechanical properties. So we need now to go a little bit inside the capability of modeling the expected properties, overall properties of the cellular solids. But before touching this topic, let's have a look to one possibility. So we can make at the end one consideration, just one possibility, to fabricate a cellular solid on a lab scale. And to this purpose, let's see together this video, which was realized inside, inside the Department of Material Science of the University of Sheffield. Let's have a look.
झिल्ली को कौन सा कौन की कहता हूँ इसे रहता है इसका कहते हैं इसकी तंबी बोल अच्छा खबर
So, okay, what to say? This is just an example.
पाता पेटा क्या भी नहीं
Somebody has the microphone open. Can close it, please?
खुदा भी bypass सका
Roshan, Roshan, can you close your microphone? Okay. This is just an example on how, in this case, on a lab scale, we can fabricate cellular materials based on metallic materials. That one was an aluminum alloy. If you have a look, let me just recover, okay, this picture. You can see that the void distribution with this technology inside the cellular solid is quite irregular. And this represents a problem when we won't go inside the possibility to model the behavior of a cellular solid. We need to assume, even though we are able to fabricate structure in this way, that the cell distribution inside the cellular solid is overall the same. And this is the main assumption which must be made in order to define some modeling approach on overall properties of the cellular solid itself. So for high performing cellular solid, we are able to fabricate cells with more or less complicated structures, which are repeated in the same way inside all the volume of the cellular solid itself. So having said that,
Prof, can I ask a question?
At the end of the lesson, please. Okay. Having said that, let's go on. If my screen is going to work, not this moment. Okay. So the properties of the cellular solids, they depends on the properties, obviously, of the base materials, such as mass density, Young modulus, when present, yielding strength, on the relative density, which is, as we will see, a very important parameter, that is the ratio between the density of the cellular solids divided by the density of the bulk corresponding material, and then by, in a short way, remembering what we just said at the beginning of these lessons, on the, let me say, cell geometry, which can have, as we said, open and closed solutions. In open cells, we do have just solid in edge, and the voids inside the materials are all interconnected. In closed cells, we do have mass, we do have materials in edges, but also on faces. And this can give different contribution to the overall mechanical properties. We said, and I want to underline again, that we are thinking about cellular solids for which the ratio between the real density of the cellular and the mass density of the corresponding bulk is lower than 0.3. And otherwise, we should talk about pores inside the solid. Now we are in this situation, and all what we will discuss is referred to this situation, which is the usual situation in real engineering cellular solids. The solids and the cells, They can be, let me say, defined on a bidimensional way, as in the honeycombs. And in this case, they can have geometry as triangles, squares, or hexagons, or they can be developed in a three-dimensional way. And in this case, we have a lot of possible combination, like, for example, rhombic, dodecahedra, and so on. They are all classified, and all the basic relations, the geometrical relations, according to the 3D cell geometry, are known and can be found on the specialized test. This is one example of honeycombs. This is one example of 3D cellular solids. Unit cells. You see here, we can define the length of the single cells. We can define the thickness of the edge, for example. These two properties are defined according to the base geometry and are very important for the following relationship. But before going inside these base relationships, we must define another concept, which is the so-called connectivity. And connectivity is based on the fact that vertices of the single cells are connected by edges, that is here, for example, connected by edges, which can also show phases only in the case, with materials on, obviously, in the case we are thinking about closed cells. And so we can define two concepts, two numbers. The first one is called the edge connectivity. The second one is called the phase connectivity. The edge connectivity is usually defined as ZE, and it represents the number of edges which are meeting at a vertex. The phase connectivity is defined as ZF, and this is a number which defines the number of phases which are meeting at an edge. Typically, but not exclusively, for foams, ZF is equal to 3. With respect to the edge connectivity, typically, but not exclusively, ZE is equal to 3 for honeycombs. Let's have a look, for example, here. You see here, at this point, 1, 2, 3 edges are converging. For foams, the value of ZE is equal to 4. But that's typically, not exclusively, in the sense that depending on the cell geometry, we can define these two parameters. And these two parameters are important because they allow to us to define a quantity which is called an average, and which is, generally speaking, and again, typically, not exclusively, equal to 5, defined as described in this formula. That is the value of ZE multiplied by ZF divided by ZE minus 2, all multiplied for 1 minus 2 divided F, where F represents the number of phases, which obviously depend on the basic cell geometry. This parameter and average, as you see, it, let me say, it is calculated, can be calculated by including the value of ZF, that is the phase connectivity. So it assumed an important role in the case we have phases with mass on in the cellular materials. So it assumes importance when we need to make some consideration about cellular solids, which are classified as closed cells cellular solids. Having said that, and without making too much demonstrations, we can define some basic relationship for one of the most important parameters for the cellular solid, which is the ratio between the real density and the density of the corresponding bulk materials, which have these expressions, as it is seen on this slide, only in the case we have a ratio which is lower than 0.3. Otherwise, we need corrections, but this is not the case for our interest in cellular solids, in which the ratio between the two density value can be put in relationship with the ratio between the thickness T and the length L. Remember, here, T and L, okay? With a constant C1, C2, or C3, depending if we are discussing about honeycomb, by open cell forms, open cell cellular solids, or closed cell cellular solids, with a square here in the case of open cells being the C1, C2, C3 material, depending obviously also on the basic geometry, that is on the geometry of the single cells. In the case of closed cells, that is the case in which we do have mass on the faces, we can define another coefficient phi, which has the following meaning. It's a coefficient which tells us what is the material distribution, the mass distribution between faces and edges. And we do have, in the case of closed cells, materials on the faces, which is defined by taking into consideration thickness, in this case the edge thickness, TF, which is the face thickness, because the edge and the face can also have different thicknesses, the value of the geometric parameter L, the value of ZF, and you see here the value of the N average parameter, which we have defined previously in the basis of this formula. For example, typically, again, but not exclusively, when we do have, as in most of forms case, ZF equal to 3 and F equal to 14 faces, the ratio between the mass density of the cellular solids and the mass density of the corresponding bulk can be written also in a more analytic way, like in this case, where we take into consideration the thickness TE of the edge, the thickness TF of the face, and the characteristic length of the unit cells. We do not have to make many efforts in the sense that all these equations comes from apart the value of the coefficient C1, C2, and C3 by geometric consideration, because we do have tables already written in which, depending on the basic geometry of the unit cells, but with the hypothesis that this unit cell is going to be repeated in the same way all inside the bulk of the cellular or inside the volume of the cellular solids, we do have the expressions of the ratio between the real density of the cellular solids and the mass density of the corresponding bulk materials. In the case of honeycombs, this force, where, for example, we have equilateral triangles as basic geometry, or squares, or hexagons. In the case of open cells, when we do have triangular prisms and so on, or in the case of closed cells, depending again from the basic geometry. So we do know, and you can find it, I said, apart from this table, on specialized tests, which are the value of ZE, of ZF, of N average, of F, the number of phases, depending on the basic geometry, and using expressions which can be reconducted to this general approach, we do have the possibility to calculate offline, which is the expected ratio between the real density of the cellular solids and the mass density of the corresponding bulk materials. This to define one important parameter, which is, as I said, the ratio between the two mass density. As we will see from now on, this ratio is very important because it can be put in relationship with some of the expected mechanical properties. And so, if we start to discuss this, that is the expected mechanical properties, the first assumption, the first thing that we have to say is that we are in presence of materials which are essentially void, so that it could configure a situation in which the amount, let me say in this way, of the defects inside the material itself is very, very high. And so we cannot expect that the mechanical behavior, which is interesting for us in terms of response of the materials to applied load, would look to the tensile properties of the materials itself, due to the fact that this material has a lot of voids inside, and the tensile properties can be, and they are, expected as poor properties. What is interesting for us is the behavior when the solid is subjected, the solid, I mean the cellular solid, is subjected to compression load. And this is the field of application of this kind of materials, when they have to resist, when they have to face with compression loads, compression applied loads. And so if we want to have an idea in terms of quasi-static behavior of the materials itself, we can have a look qualitatively just to identify the most important phenomena which can happen and which will allow to us to make some consideration. We can have a look to the stress-strain diagram, stress-strain response of the materials when it is subjected to compressive stress. And we can have, generally speaking, we can have, just to categorize, three different classes of behavior. The first diagram here is that which is referred to the diagram when we have the material, the base materials, which is going to not show neither a brittle behavior, neither, let me say, a plastic behavior. So is, for example, the case of materials which behave essentially elastic, not exclusively linear elastic, but essentially elastic till rupture. For example, as in the case of an elastomeric base materials. What we can see here, we see that as it always happens for all materials we know, applying the first stress, compressive stress, we do have a linear elastic response of the material itself. Then, when we apply a stress which is higher than a critical stress, sigma as here representing EL, that means elastic, we can enter in a field of very broad deformation in compression, obviously, of the material itself, which is related, as we will see later, to the possibility of having a sort of elastic instability, what we call buckling of the materials itself. And this phase, which represent a characteristic part of the behavior of the materials itself, is, let me say, a phase of behavior in which we have very relevant strain values with very low, at least near to zero, so that we can write here, it exists a plateau with very low increase of applied stress. And this behavior is going to be shown by the materials itself till not infinitely. Remember, we are compressing the materials till a limit value of deformation, which is called epsilon D, strain epsilon D, in which, due to compression, we have recovered, we have eliminated all voids inside the cellular solids, and so we have densificated the material itself. So this value of limit strain epsilon D is the limit strain epsilon in order to have D, which stands for densification of the materials itself. This is the first behavior that we can expect when the base materials essentially behave elastically till the densification phase. But since we have said that we can have also, as we saw in the video, cellular solids made by metallic materials or metallic alloys, in this case, we cannot expect an elastic behavior till densification and then rupture, because we know that metallic alloys, they are characterized to a different extent, depending on the alloy itself, by the possibility to have plastic deformation. That is, to the possibility to have non-recoverable deformation due to yielding of the materials itself. And in this case, what we can expect is related to the first part of the behavior, which is always the same, because it, let me say qualitatively, not numerically, it expresses the linear elastic response of the materials, unless we reach all the limit for buckling, or, as it always happens, the limit of plastic yielding of the materials itself. And also in this case, when we reach a plastic yielding, we do have, for very, very limited, at least something near zero, increase in applied compressive stress, a very relevant increase in strain up to, again, the final limit, which is again defined as epsilon d, strain d, in which densification due to recovery of all the voids inside cellular solids starts to happen. The last, so this is the, let me say, first one, the qualitative behavior which we can expect for base materials fabricated as cellular solids having an elastic behavior through densification, till the densification happens. In the second case is the case related to the fact that we can have a base materials used to fabricate the cellular solids having an elastoplastic behavior. So not only the elasticity, linear or some non-linear elasticity, but also yielding of the materials. And the third behavior we can expect, talking generally, is those in which we do have elastic behavior till densification and rupture, but the base materials, it show a brittle behavior, like, for example, in the case of ceramic-based cellular solids. Now, in this case, what we can see, first of all, we have again the fourth part of the stress-strain diagram in which the linear elastic response is going to be the answer, is going to be the response of the materials itself. Then again, we can expect, being in compression, that we can reach the situation in which we recover all the initial voids, and thus densification itself, again defined with a value of strain epsilon d, where d stands again for densification. But we do have, as you see here, a more fragmented diagram, even though when we reach the limit stress for the elastic behavior of the materials itself, we can have without significant increase in applied stress, a very relevant response in strains. A sort of plateau also in this case, but is a sort of interpolated plateau due to the fact that the curve is very fragmented. And why we do have this fragmentation? And we will make, and we will recall this concept more deeply when we will make some further additions on the behavior of ceramic materials, because we are discussing about unicells like this one. So let's have a look to this, just one, the first one. And let's think that the base materials is a ceramic materials. Well, here we do have a sort of beam. When we put a load on the cellular solids, this is a reticular structure. And being a reticular structure, one of the general rules of the reticular structures is that the beams, they are subjected inside only to compression or tensile stress. But we know that when we think and we are discussing about ceramic materials, they do show a very wide scattering in terms of strength due to the unreproducibility of defect linked to the fabrication processes. And so this means that here we start, just to explain to you, for example, the force beam, then the load is redistributed between the other one, then we reach again the strength, and thus the rupture of another beam of the single cells, and we do have this fragmented answer in the case which we think that the base materials is characterized by an elastic, brittle materials behavior. Now, let's have a look to the cases we have discussed here. And essentially, for the first case, that is the case in which we have linear elasticity and then buckling, and the second case in which we have linear elasticity and then yielding of the materials. Because our purpose is, to some extent, to identify the limit stress for which the buckling is going to occur and the yielding is going to occur. So we will not discuss the case of elastic brittle film because actually the most important in terms of applications are those related to the first of the second general behavior. We need, apart from this general description, also to take in mind, we cannot forget that, generally speaking, the answer of the cellular solids is different in the case we have open cells or in the case we have closed cells. So we must keep with us this distinction when we are going to identify the basic behavior in terms of critical stress. Well, linear elasticity, that is the first part of the answer in compression. Case of open cells with small strains, which is going to represent the existence of the linear elasticity behavior of the material itself. The basic parameter which can be used to describe, in case of a linear elasticity, the behavior of the single cell are the Young modulus of the cellular solid, the shear modulus of the cellular solids, the bulk modulus of the cellular solid, which can be identified as the Young modulus when an homogeneous distribution of the cells is performed inside the materials, and the Poisson coefficient mean. Well, it can be demonstrated, and you can trust me, and let's have a look to the final situation, that the ratio between the Young modulus of the cellular solids and the response of linear elasticity, so the ratio between the Young modulus of the cellular solids, which is the quantity we want to know, and the Young modulus of the corresponding bulk materials, as well as the ratio between the shear modulus of the cellular solids and the Young modulus of the corresponding bulk material, as you can see here, they can be put, depending on a parameter, which is a constant, linked to the distribution, the size, the geometry of the unit cells, repeated inside the volume in the same way, can be put directly in relation with the ratio between the mass density of the cellular solids and the mass density of the corresponding bulk materials by using this constant, which are tabulated. That means we have tables for that, depending on the size of the single cell, which is the ratio we have defined before. So the reason because of we put, this is the first one, most attention on where it was, I don't remember, no, later on. Here, I see, on the definition of a general rule, which is possible, between the ratio of the two density according to the basic geometry of the cells, is that if we are going to discuss, like here, the linear elastic behavior, having defined this ratio, we can estimate, knowing the properties of the bulk materials, the Young modulus and the shear modulus of the cellular materials itself. And for what it concerns the Poisson coefficient, it also can be defined in such a simple way by using the two constants C1 and C2. Just a curiosity for you, it can happen, and that depends on the geometry of the single cells, that this value of the Poisson coefficient is lower than 0, which is not possible in conventional materials, but it can be possible in the cellular solid area. This does not mean that the base materials with which we have fabricated the cellular solid changes its properties from Poisson coefficient near 0.3 to Poisson coefficients lower than 0. But the overall answer of the structure, depending on the way in which all the beams are going to be deformed, can result in the direction of load application in a Poisson coefficient which is lower than 0. And this means, I can remember to you, that if we say that the Poisson coefficient is lower than 0, when we are going to apply a compression, we do have an expansion. And when we are going to apply, generally speaking, a tensile load, we do have a contraction, which is not the common way in which conventional materials, the engineering materials, bulk materials that we know, behave. But I repeat, this effect is not related to the fact that the base materials has changed its fundamental properties or answer, that is, each time we put the materials in a tensile mode, it has an elongation and vice versa for compression, but it's just a result of internal deformation of the beams, which are the basic elements of the cells of the cellular solid. So by knowing the ratio between the two mass density and the constant C1 and C2, we can have a direct estimation of the Young modulus and of the shear modulus and of the Poisson coefficient of the cellular solid in the case, this is referred to this case, we do have open cells. What is going to happen? What is going to happen if we move from the open cell case to the closed cell case? Always, if you want to have an idea of the linear elastic response, linear elastic behavior in case of small strains, which are synonymous of linear elasticity. Well, the main difference between this configuration here reported geometrically, for simplicity, is a cube, okay? And the configuration which is reported here, which is again a cube, is that in the case we do have closed cells, first of all, we have mass on the faces, you see here. This is also the meaning, you see TE and TF, that we have parameter that we have defined here. TE we have defined as the edge thickness, TF as the face thickness, and generally speaking, they can be different. So we do have contributions, a flexural contributions due to the membrane bidimensional stress state on the faces, which to some extent, being a material to be deformed, add resistance to deformation due to the applied load. But we do have also another effect that we must keep, generally speaking, we must have in mind, we cannot neglect, generally speaking, that is the fact that inside these open, closed cells, we do have, for example, air. I mean, we do have atmospheric pressure, so we do have a fluid. So that when we are going to compress the cells, we do have the compression of the fluid, which is in the closed cells, which offer again resistance to deformation. So we do have the basic contribution of the edges, but in addition, we do have the contribution in terms of resistance of the faces, and we do have also the contribution in terms of resistance due to the compression of fluid, which is inside the closed cells. Thus, having in mind this, we can have, and also in this case, I want to skip for you the general demonstration. Two very simple, I would say, formula for which and with which, again, we can estimate the Young modulus and the shear modulus of the cellular materials for the linear elastic behavior, in which, if you see, we do have, again, the dependence on the ratio between the mass density of the solid, rho s, corresponding bulk, and the mass density of the cellular cells, as in the first case with open cells. But we do have also the phi parameter here in this formula, which I want to recall to you, I go a little bit back, is this parameter, which has been defined as a coefficient which can be calculated by knowing and defining the thickness of the edge, the thickness of the face, the unit length reference of the cells, the number of phases in terms of connectivity, ZF, and N average, which was defined by this formula, because obviously, we must take into account that we do have also the resistance which is offered by the materials which is allocated on the faces of the unit cells. And so these are the basic relationship in which at this stage you do not see any special contribution of compression of the fluid inside, which can be at a first extent in the case of small strains, the linear elasticity also be neglected, but which will be not, can be not neglected when we are going to increase the deformation of the cells. So when we are going to move, for example, in the phase of buckling or in the phase of plastic yielding of the base materials. So with these two very simple relationship, with our assumption, we can have an evaluation offline of the elastic properties, elastic parameters, which are going to define the answer of the cellular cells here or here, in the case of elastomeric behavior or elastic plastic behavior, but just limiting to the linear elasticity of the materials itself, differentiated in the case we have open and in the case we have closed cells. The first step is to understand if these relationships are going to work well. Well, and this is the reason because I can skip the demonstration with you, because that's not the purpose of our courses. The answer is yes. These are some experimental data. In the case of linear elasticity, for the Young modulus, for the shear modulus, the dotted line are referred to open cell bulbs, which are listed here. The continuous line is referred to closed cells situation. And as you can see here, the experimental data, which are obviously differentiated according to the base materials, fit well or are well fitted by the simple equations that I showed to you and which can be used for the pre-dimensioning of the cells according to the properties, overall properties that we want to achieve in terms of response of materials. What is going to happen when we enter in the non-linear behavior? And let's have a look first of all to the possibility to have buckling of the materials, in which we can have elasticity, but this is no linear elasticity. Obviously, also in this case, we need to give two different relationships depending on the fact that we do have open or closed cells. That is, cells in which response is essentially governed by edges, beams, and cells, closed case, in which the answer is governed also by mass, which is distributed on the faces. Well, we can define the limit elastic stress for collapse, for buckling of these structures, and this can be calculated theoretically by remembering the Eulero approach to buckling. But nevertheless, in the case of an open cells, the limit elastic stress for buckling divided by the bulk modulus of the Young modulus of the corresponding bulk materials, ES, is again, as you can see, a function that's very complicated, apart from this coefficient C4, which is again tabulated, of the ratio between the mass density of cellular solids and the mass density of the corresponding bulk materials. So again, knowing the value of C4, knowing the value of the unit cell geometry, we are able to define which is the value of this ratio. And so we are able to identify the elastic stress in which buckling is starting to occur. That is, for example, this point in which buckling is starting to occur. Well, when we move from the open cells to the closed cells situation, we can again define, let me say with a similar approach, the value of the initial elastic stress for buckling, the first equation here, sigma EL, which is again something depending on the ratio between the two mass densities as before, but we cannot skip in our consideration the resistance which is offered by the fluid inside the material, inside the cells. And so you see here, a pressure term is going to be put here. Then this says to us also another thing, that we have as here an initial point for the open cells in which buckling is going to occur. But if we want to increase our strain, we need to increase, even though not to an extent which is very, very high, the applied stress, because the contribution of the resistance which is offered by the fluid which is entrapped inside the single cells, and thus inside all the cells, is going to be increased when we are going to increase the compressive strain. And thus we can define, according to the strain in compression deformation, the value of the stress, which is more or less represented as a plateau. We do have an increase, but not very relevant. But in any case, this is the right approach, which allow to us to describe also the behavior after buckling when we are in the case of closed cells. And again, you can see here, apart from the contribution of the fluid resistance due to compression, and we can consider in this case that the behavior is that of an ideal gas, we do have values which are related to the ratio of the two mass density. This for the buckling. Okay, so the buckling in the case of open cells, the buckling, and then the slow increase in stress, which we call here plateau, in the case of closed cells. Does it work? Yes, it works. That's another example of fitting of experimental data in the case of closed cells, continuous line, and in the case of open cells, dotted line. For what it concerns, you can read here on the y-axis, the relative elastic collapse stress, that is the start of buckling. Relative because it is divided, as it's written here, and as it is written here in the formula, by the Young modulus of the corresponding bulk materials. Something similar to this approach can be also defined and used when we want to define the limit stress which is going to control the plastic behavior. And then this means that we are discussing, for example, about this situation in which the base materials is able to show an elastoplastic behavior that is yielding, it has a yielding strength. And so also in this case, now it should be, let me say, quite clear, the scheme. We need to, it's a little bit complicated by a theoretical way, but in any way, we need to define the case in which we do have an open cell and the case in which we do have a closed cell. We can define the limit stress, what is called here sigma PL, that means for starting the plasticity behavior in both cases. And also in this case, you see they are ratio with the yielding strength of the base materials, and it is directly related, can be put in a direct relationship with the ratio of the two mass density value, apart some known coefficient, here called C5. In the case of closed cells, we have a simple, open cells, we have the first simple equation. In the case of closed cells, we have, again, I would say the simple equation, but in which, again, like in our previous examples, we do have the phi coefficient, which is the coefficient which tells to us something about the mass distributions on edges and on faces, because also in this case, we do have to consider the resistance, which is the response, which is offered by the mass, not only allocated on the edges, on the beams, but also existence, but also on the faces of the single cells. But with this very two simple relationships, we can have an idea and we can have an estimation of the value of the stress, compressive stress, to be applied in order to start plastic deformation of the single cells, that is, of all the cells inside the cellular solids, having assumed at the beginning that the distribution of the cells is the same in all points of our cellular solids. Again, does it work? Yes, it works. Here you have some experimental data which are fitted by using that simple equation. What is going to happen then after the phase of extended buckling and deformation and the phase of extended plastic deformation is to let me go back, is to it's going to happen that the densification due to the progressive deformation of the cellular solids is going to be shown, so that from this point ahead, after the densification strain of the cellular solids, we do have still a response of the materials, but this response is not interesting for us in the sense that we do not have more the answer of a cellular solids, because the material has been densified by recovering, by eliminating all voids. And now the question is, we have defined, generally speaking, a densification strain. Does it exist, like in the previous case, a simple relationship in which, or with which, we can predict or we can identify the expected densification strain of the cellular solids? And the answer is yes. You see here, the answer is yes, and in most of cases, and this is the situation referred to practical application, again, the densification strain has a very simple formulation, 1 minus 1.4, which is going to multiply the ratio between the two mass density, the mass density of the cellular solids and the mass density of the bulk corresponding materials. So you see here that we have the possibility to use, let me say, quite a simple approach to predict the expected macroscopical properties of this special class of materials, and in which, for these properties we have seen up to now, the relevant parameter is the ratio between the two mass density, which can put directly in connection with the geometry of the cell, that is the cell shape, as we told at the beginning, And thus, by defining the cell shape, by defining obviously the base materials we are going to use, by looking to the geometrical parameter which are going to characterize the cells, we are able to calculate the expected ratio between the two mass density, and we are able to define, according to this simple model, the plastic collapse stress in the case we have a base materials showing yielding, divided into the case we do have an open cell or we do have a closed cell, as well as here the collapse stress for buckling in the case we do have an open cell or in the case we do have a closed cell, as well as the values of the Young modulus and the values of the shear modulus in the case of closed or in the case of open cells, if we are going to look to the linear elastic response of the cellular solids. With this, we can then move on to make some consideration about potential applications of this special class of materials for our purposes, not generally speaking. And we have all the basis to understand what we will start to discuss from next lessons, next Friday, which will tell us why and how these kind of materials are very interesting for us to be used, for example, as energy absorbers. But this will be the topic of our meeting on next Friday. So for today, okay, I think we can stop here. Now, if somebody has some questions, please, I am here to answer. Do you have some questions? Okay, if no questions, I can greet you and see you on the lesson of next Friday. Good afternoon to everybody.
Buona serata, professore.
Arrivederci, arrivederci. Arrivederci.